an Internet of Things platform for production monitoring in the aerospace manufacturing industry. From the Journal of Cleaner Production, Volume 368, September 25, 2022. By Daniel Rodrigues, Paulo Carvalho, Solange Rito Lima, Emanuel Lima, Nuno Vasco Lopes. Introduction. Industrial Revolution has undergone several disruptive generations ranging from steam-powered mechanization, electricity-powered mass production, computer-based automated production to cyber-physical systems CPS and Internet of Things powered production. The next generation, known as the fifth generation, production will be sustained by intelligent automation AI-powered systems. This means that the industry of future will certainly be more automated and intelligent in the way manufacturing processes as well as business management decision-making are carried out. That intelligence will forecast distinct production scenarios and will recommend the most adequate solution for each particular scenario to increase production and or answer clients' demand and needs. Simultaneously, intelligence will optimize and increase the efficiency of manufacturing process, giving clear information about the processes, equipment, product, and operators. Some of the main challenges that industry will face in next years include CUSIAC 2018, Erkan and Gursev 2020, Thoban ETRL 2017. A. Digital transformation. The adoption of computer systems to streamline the different production, logistics, and administration processes is increasingly required in many types of industries. B. Optimization. One of the main problems present in industry is the inefficient use of resources, such as waste of raw materials, inefficiency in scheduling processes, inefficiency in using energy, etc. C. Cybersecurity. Given the increasing level of digitization in industry, the consequences of a lack of security measures can be devastating for business. Protecting the systems and data from potential attacks are therefore mandatory. D. Horizontal connectivity. The connectivity between organizations for transaction purposes, along with value chain in the digital space, is a major trend. The connection of different systems will allow an enhanced cooperation between companies through shared services, resources, and data. And E. Automation. Artificial intelligence is increasingly being applied to manufacturing industry for automatizing tasks, setting parameters automatically, optimizing processes and operations, scheduling production, and for supporting decision-making through detailed data analysis. Several initiatives related to the development and application of Internet of Things and CPS systems, such as Industry 4.0 Kagaman 2013, have emerged recently. In this sense, in recent studies, the International Data Corporation IDC predicted that investments related to industrial Internet of Things worldwide may exceed the quota of $1 billion in 2022 Turkey and Shire 2019, with the manufacturing industry being one of the sectors with greater growth. The business model and production process of the manufacturing industry can benefit greatly with the integration of Internet of Things and CPS systems, as it allows the automation and optimization of assembly line processes, lowering the production costs. Moreover, it allows to improve the production quality, to offer product customization, and the ability to adjust to market responses by demand due to ETRL 2022, Kagaman 2013. Despite the growing interest in the area, the adoption and integration of Internet of Things technologies in industry's business and production systems still present many challenges. This article proposes an Internet of Things architecture for monitoring the production line of an aeronautics company with the aim of helping to mitigate the aforementioned challenges. A case study of the proposed Internet of Things architecture has been conducted at Embraer, Portugal. with the objective of monitoring a production line and measuring the production and assembler times. Initially, these tasks were carried out manually by the operators through a shared spreadsheet, and, therefore, very prone to human errors. In this sense, the proposed solution implements an Internet of Things system, with respective sensors and actuators, to assist and improve the monitoring methods in place, making the overall process more efficient and less error-prone. The new platform takes into account interoperability issues with the existing database systems and methods used for data collection. Before the deployment of the proposed solution in the shop floor, a proof of concept has been conducted and tested in diverse lab scenarios with the production line historical data. In our view, the present Internet of Things system proposal and case study bring an added value to existing and new solutions for monitoring delays in manufacturing and production lines, namely, through the use of a generic data model and integration insights of legacy monitoring approaches with open source platforms e.g. Firmware. This approach can ease the use of different Internet of Things devices in the manufacturing industry, crucial for the Industry 4.0 and 5.0. This article is organized as follows. Section 2 discusses related work on Internet of Things and CPS solutions. Section 3 characterizes the case study, highlighting the monitoring methods, elements to monitor, related work, and current limitations. Section 4 presents the architecture of the proposed solution, its components and corresponding interactions, and development issues. The test scenario and the monitoring results obtained from the validation tests are discussed in Section 5. Finally, Section 6 summarizes the final conclusions and future work. Background and related work. In recent years, the potential of Internet of Things in the aerospace industry has been exploited at both ground and air operational levels. The number of Internet of Things solutions to assist more robust and efficient performance and services monitoring has also grown with the perspectives opened by Internet of Things. Ramalingam et al., 2017. The manufacturing industry is one of the sectors with the greatest interest in the integration of Internet of Things and CPS systems. Druot et al., 2019, Kagaman, 2013, Liu and Yu, 2013. Converging distinct technologies and sensors in their business and production models. Wayno et al., 2020, Kai et al., 2019, Erkan and Gursev, 2020. Guyan et al., 2019, Hassan, 2018, Jutin et al., 2022. An example is the use of radio frequency identification (RFID) sensors integrated into IT systems for managing logistics resources, which allows the monitoring of product movement in real time and the instantaneous acquisition of associated data through wireless communication infrastructures. Kievanpour and 8 Cardi, 2019, Sontonino et al., 2018, Shaolin et al., 2012. Another example is related to using sensors to monitor processes in production lines or providing more in-depth analysis of these processes with the aid of computer vision technologies, machine learning (ML), and big data. Churati et al., 2019, Meyerhofer et al., 2019, Sophie et al., 2019, Luxemburger et al., 2019, Kedar et al., 2019, Paras et al., 2020, Ruiz et al., 2020. These technologies enable a better evaluation of the quality of products, the identification of failures and inefficiencies, and the evaluation of equipment condition. As an example, Luke and Booth 2018 reports that computer vision technology and ML have been used to identify production defects in additive metal manufacturing. Najwan et al., 2019, Romero and Vieira, 2016. Regardless of the sector, Some problems are transversal to any project that intends to incorporate Internet of Things systems. One of these issues is the interoperability among devices and systems that constitute the Internet of Things solutions, in terms of types of communication, protocols, data formats, etc. In addition, there are scalability problems regarding both the number of devices the Internet of Things system requires or aspires to have, and the increasing amount of data that is capable of producing, which results in an additional computational effort in processing this data. Furthermore, the requirements in terms of responsiveness and efficiency are increasing, both in computational terms, especially when it comes to edge and fog computing, and in terms of energy consumption. Korchagin ETRL 2019, ETRL 2014, attending to the conditions or environment in which the devices are deployed. Finally, with the growth of Internet of Things systems and their adoption, the security risks also increase, especially regarding the security of devices, communication networks, and data. Luigi ETRL 2020, Jutin ETRL 2022. One way to mitigate these issues when developing an Internet of Things system is to use Internet of Things platforms that aggregate the necessary and appropriate components. Nowadays, there is a vast number of available platforms and middleware, even considering uniquely open-source solutions, e.g., Ponte Eclipse, OM2 Meclipse, Alea ETRL 2014, and Fireware Flavio ETRL 2019. These solutions have significant differences from their purpose to the type and format of messages and protocols supported. Therefore, they should be selected according to the particularities of each case study. The existent solutions for the analysis and presentation of available data also significant. For example, Microsoft Power BI, Tableau, Spotfire TIBCO software, and SaaS are solutions that have recently stood out in the market. House and ETRL 2019. The open-source Grafana visualization tool is also frequently used in the Fireware environment. Facing this, the selection and integration of these systems require a careful analysis of the environment to be monitored and its requirements in order to identify the platforms and technologies that best suit each case. The design and application of these systems in manufacturing industrial environments is still a problem requiring further study. Therefore, the present work proposes the design of a generic Internet of Things platform that aims to increase the monitoring capacity and that takes into account the integration between the Internet of Things system and the Manufacturing Execution System MES. Additionally, for the application of the platform, a production line from the world leader in aerospace manufacturing, Embraer Portugal, was used as reference. The expectation and aim are that the application of Internet of Things and CPS systems can significantly optimize industrial processes, making the system, as a whole, safer, more resilient, more flexible, and less dependent on human action. Case study characterization. The manufacturing industry urges for efficient and automated production processes. These processes are critical in the aerospace industry, as many lives depend on fully reliable and robustly produced aircraft parts. As mentioned, the proposal of an Internet of Things solution to assist the real-time monitoring and assessment of the involved production processes is the goal of this article, which takes a leading company in this field, Embraer Portugal, as a case study. The production of aircraft parts at Embraer is carried out along production lines, constituted by different production stations, in which the operations/tasks for the production of the different parts take place. For each different aircraft part, there is a set of specific tasks and a sequence in which these tasks must be performed in order to obtain the final product. Life cycle of production orders. Production processes are divided into two categories: orders and operations. Orders for production define the sequence of operations that must be performed in a production line for the elaboration of a component or final product. Operations correspond to the tasks performed in the production stations, which may require the direct or indirect intervention of operators. These operations can be manual, automated, or combinations thereof, depending on the type of tasks that are associated with them. In more detail, the unreleased state represents the initial state of the life cycle in which an order entered the MES, without execution parameters defined, namely the start and end dates. In the scheduled state, the order is allocated to the production line with the appropriate execution parameters assigned. The available state indicates that the requirements for starting the execution of the order are satisfied, and it can be started or resumed in case of the execution has been previously interrupted. The run state represents the order running, indicating that the operations associated with it are already allocated to a particular production station or are already being executed. The on-hold state indicates a pause in the production cycle. There are several causes for transiting into this state, such as lack of materials, non-conformity, among other situations that prevent the order execution from proceeding. This state normally implies an extended pause before resuming the execution of the order. Finally, the terminating states cancelled and complete indicate the end of the cycle of an order. The corresponding transitions occur when the order is cancelled, or the effective production of the component/final product is successfully accomplished, respectively. Ideally, an order life cycle will follow the sequence of states: unreleased, scheduled, available, run, and, finally, complete. However, the probabilities associated with a change of state indicate that a normal sequence may not occur. As shown, compared to production orders, maintenance orders are nearly twice as likely to move to an on-hold state, causing delays that impair completing the order in the expected time schedule. Life cycle of production operations. Despite the similarities, some exceptions occur, namely the number of operations transiting from the run state to the on-hold state, which is significantly lower, and the percentage of operations transiting from the run state to the complete state, which is significantly higher. The suspended state results from momentary interruption of the operation's execution. Unlike the on-hold state, this state is checked when the operation is expected to be resumed after a short period of time. Regarding transition percentages, operations transiting from suspended to run state are close to 100%, never requiring intermediate transitions back to the run state. Conversely, operations transiting to the on-hold state always require an intermediate state before returning to the run state. As mentioned, there are few transitions from the run to the on-hold state, despite the suspension of a significant number of operations. This behavior is considered normal, as certain operations are expected to be suspended for reasons related to working hours or reasons requiring a momentary interruption of the operation. This effect is stressed by the execution time of operations, which in certain cases may span multiple working days. Manufacturing Execution System (MES) limitations. The production line for manufacturing an aircraft component involves manual and/or automated processes carried out in a single or distinct production stations. These processes are continuously monitored in order to evaluate production indexes and to properly react in case of an irregularity is found. This constant monitoring allows a convenient evaluation of all processes, being crucial for minimizing costs of deviations and maximizing productivity. The MES is the integrating infrastructure that conveys all relevant events of processes, production lines, and operators, recorded throughout the production cycle. This system allows to store and analyze the context of execution and the corresponding production measures, For instance, the time spent in each production station. Despite its undeniable relevance to assist production monitoring, several limitations of the current recording procedures need to be addressed to improve the production rate, minimizing inefficiencies, irregularities, and costs. Currently, monitoring the production cycle is limited to state transitions of operations, e.g., from the available state to the run state. However, as the state transition is dependent on the operator interaction with the production station terminal, the process is time-consuming and prone to errors. The interaction operator station terminal occurs in distinct production stages, and, depending on this interaction, the MES automatically assigns the operation state. For example, when an operator consults the list of instructions for an operation, it is determined that the operation is running, and its state is changed to run. Similarly, when the operator opens the list of instructions for the next operation, the state of the previous operation is considered complete. This dependency on the interaction between the operator and the station terminal leads to a monitoring process with a human-determined granularity. Thus, when operators do not follow the established protocols or make mistakes, monitoring errors may occur. The following example illustrates a clear interference with the measurement of execution times. If an operator starts an operation without opening the list of instructions from the previous one due to failure or familiarity with the instructions necessary to perform the operation, the system assumes that the previous operation was executed in a much shorter time interval than the real one. Additionally, as the information available is only about state transitions, monitoring the progress of processes continuously is very limited. For instance, detailed information regarding the development of operations within the state of run is unavailable, which limits the real-time analysis of their execution. Facing the identified limitations, the automation of monitoring procedures in production stations reveals to be crucial, and the integration of Internet of Things in the existing infrastructure is a convenient way to achieve it. The deployment of an Internet of Things system, with sensors and actuators in the production lines, will allow solving the problem associated with the real-time evaluation of operations execution time, pointing out deviations for subsequent correction. Although part of this monitoring is currently performed manually, the existing infrastructure does not provide a sufficient level of detail for delay analysis. In particular, no data is collected on the progress of processes during their execution, which impairs a real-time delay follow-up, and the current infrastructural acts of means for managing the Internet of Things devices required for monitoring automation. In addition, the fact that MES orchestrates the automation process, it creates complex challenges when working with several legacy systems that were developed by different vendors and standards to address different segments of the manufacturing process. Proposed Internet of Things system. The proposed Internet of Things solution aims at monitoring the production process, in particular, the processes running in the production stations, assessing production delay through the ubiquitous integration between the Internet of Things system responsible for monitoring the production line and the MES, which is responsible for storing state information of both processes and production line. In this section, the architecture of the system will be presented, describing its main components and the interactions between them. Important design goals are the modularity and scalability of the system components regarding the introduction, in the future, of new monitoring requirements and features, such as the quality of manufactured parts. Architecture. The architecture of the proposed Internet of Things solution, integrating the Internet of Things monitoring components with the components in the MES infrastructure system, is represented in Fig. 4. The development of the Internet of Things system relies on the open-source platform Firmware. Flavio et al. 2019. This choice is grounded on multiple arguments, including the wide variety of tools, application flexibility, documentation and support available, and its growing relevance in the Internet of Things market. As shown, the architecture of the production line monitoring system consists of 4 layers: physical layer, data aggregation layer, data analysis layer, and, finally, the presentation layer. The layers divide the multiple components according to their context and functionality. The proposed architecture is fully modular regarding its components, from the MES to the visualization application. At lower level, the physical layer includes devices that interact with the physical environment, such as sensors and actuators, similar to any Internet of Things architecture. In addition to Internet of Things devices, pre-existing legacy sensors and other physical/digital elements, e.g., notification-based alarms, are also part of this layer. As represented, devices either generate data through sensor measurements or consume data in the form of commands over actuators. The aggregation layer contains the elements that integrate, structure, and store data, such as the databases, the broker, and the data integration component. Data integration takes place at this layer, i.e., data coming from the MES is integrated with data coming from the Internet of Things devices. In the broker, this is carried out by the integration component that acts as an interface between the MES database and the broker. This data integration process is essential for bridging the gap between the Internet of Things and production system, associating sensors measurement data with data from the respective production stations and monitored processes registered in the MES database. The data analytics layer includes the data processing modules for assessing parameters such as production delay, production level, and product quality assessment, among others. The analysis can either be carried out in real time, if the response time is essential, or by request, if needed at specific times. In this case, monitoring encompasses all the real-time analysis processes of the system, such as the delay analysis, for the performance index analysis, or key performance indicators KPIs, or root cause analysis RCA, as do not have real-time requirements. They are provided on request or at predetermined intervals. Examples of these indicators are product profitability and time to market, among others. In addition, monitoring can automatically activate alarms and actuators if certain conditions are met. As for RCA, the aim is to identify causes of failures or inefficiencies in the system. Finally, the presentation layer is responsible for presenting the results obtained from analyzing the data processed and structured at the lower layers. These results provide an up-to-date view of ongoing monitoring to assist decision-making. This layer can also receive monitoring alarms, integrating them with the visualization applications, or perform other actions, such as audible alarms or email notifications. Entities/data structure. The entities described in this section correspond to digital representations of elements in the broker, which may or may not be physical. As illustrated in Fig. 5, the entities contain a set of data. I. The attributes, which indicate the state in which the entity is, and II references to other entities, in case they have any relevant correlation. These attributes can be static or dynamic and result from one of the 3 components that interact with the broker: the Internet of Things agent, the data provider, or the delay analysis. Additionally, if the entity contains an actuator, commands are available for interaction with the related component. In this case, the entities correspond to the elements of interest for monitoring production lines. Among these entities are the production line processes, production stations, and sensors. Production order. The order entity consists of a set of processes necessary for the production of a part or final product. The most relevant attributes of this entity are current operation, schedule delay, progress delay, and progress. The current operation represents the operation that is running at the time of the last update. The schedule delay and progress delay represent the delay in relation to the initial scheduling date and the current progress of the order, respectively. Finally, the attribute progress corresponds to the current progress status of the order. Operation. The operation entity identifies the process taking place in a production station. As previously explained, operations are associated with an order, and each operation represents a set of tasks necessary for the development of the final product. The more relevant attributes in this entity are the identifier of the order to which the operation is associated with, the identifier of the production station in which the operation is executed, the effective start and end time of execution, and the estimated execution time. Regarding the data required through the MES database, there is the production status of the operation, the number of working hours, and the date of the last update. The production state of the operation, as the production state of the order, represents the production state in which the operation currently is. Finally, the progress and progress delay attributes correspond to the data resulting from the delay analysis. While progress represents the effective progress of the operation, progress delay indicates whether the operation is delayed or not regarding the expected execution time. Production station. The production station is the place where a particular set of operations is performed. The most relevant attributes of this entity for the case study are the production station identifier and its description. This identifier is used as a reference both in operations, as it identifies the place where the operation is carried out, and in progress sensors, as it identifies the origin of measurements. As for the description, this is normally used to describe the type of tasks which the station is associated with. Both attributes do not change during execution. Progress sensor. Generic progress sensors are an abstract representation of the sensors responsible for monitoring the progress of operations. Although the attributes of this entity depend on the characteristics of each sensor, the following attributes are always required to monitor operations: sensor identification, operation identification, progress measurement, and the date when the measurement was taken. The identification of an operation can be obtained indirectly, namely through I, the associated time stamp, II the production station where the measurement was performed, and III the operations data required at that time instant along with the respective production station. However, identifying the operation being monitored must be an unambiguous process. Otherwise, the measurements cannot be associated with the respective operations. In the present case study, the above approach is not practicable, as multiple operations may be under execution in the same production station simultaneously. Therefore, the operation must be identified by the sensor in the measurement process. Components. This section describes the main software components used in the development of the proposed solution. Of these, the data provider and delay analysis components were developed specifically for the case study. Internet of Things Device and Internet of Things Agent. The Internet of Things Device comprise the set of sensors and actuators in the system. The sensors are responsible for measuring values of the environment under study, whether physical or digital, and notifying consequently the Internet of Things agent of changes in its state. The actuators enable the execution of specific commands in order to perform an action in the environment. In this case study, only the progress sensors used in monitoring the execution of production processes are considered. These elements are not only important for the structuring of the Internet of Things system, due to the segmentation of Internet of Things devices by different agents, but also allow interoperability among different communication protocols and message formats. Internet of Things devices can communicate using different protocols, such as HTTP or MQTT, and support different types of data formats when exchanging messages, such as ultralight or JSON, which may not be supported by the entity broker. For these reasons, the Internet of Things agent is essential for handling this type of communication, assuring interoperability. Additionally, the generation of actuator commands and the corresponding forwarding of execution requests are also responsibility of the Internet of Things agent. The MES database. The MES database, corresponding to the main data infrastructure already existing in the system, stores data about the production line and related processes, such as orders, operations, and production stations. The ability to integrate Internet of Things data with data already collected by MES is crucial, as it allows to increase the capacity of monitoring the manufacturing process significantly, allowing a more effective response along production. Data provider. The data provider, as its name suggests, has the functionality to provide access to certain data sets in the system. This component works as an interface among the system components, providing the data of interest and the elements being requested. It performs filtering and processing according to the existing requirements. Its usefulness is especially relevant for the interaction among different system components, in which compatibility problems are usually present, or the direct access to data storage services is unwanted or even impractical. In this case study, the purpose of the data provider is to collect data of interest from the MES infrastructure and its subsequent integration into the broker. It should be noted that direct access to the data is impractical for the broker, as it does not have, by itself, the means to perform this interaction. Additionally, there are also compatibility problems, namely in terms of data format. In fact, the format used by the broker NGSE format is structurally different from the format obtained from searches in the MES. Broker. The broker is the central element of the Internet of Things system, and also of the overall proposed system, enabling access to monitoring data from the remaining system components. This element is responsible for creating, updating, and managing the entities of interest in the system, including, in this case, orders, operations, production stations, and progress sensors. Data access can either be direct, through an access request issued by a client to the broker, or through publisher and subscription mechanisms. In the first case, the interaction between the client and the broker is punctual and only serves to access the data set of interest at the moment the order is placed. Whereas, in the second case, the client is interested in knowing how the state of the data set of interest evolves over a certain time period. Upon subscribing, the client is informed of changes in status affecting the data set of interest whenever the subscription conditions are met. Additionally, the broker is also responsible for providing access to the Internet of Things devices associated with it through the Internet of Things agent. Delay analysis. Delay analysis is the component responsible for monitoring and analyzing the collected data and tracking the processes associated with the execution of orders and operations. The analysis is carried out by comparing the current execution time of the production processes with their expected execution time. Depending on the magnitude of time differences, a process can be considered delayed, early, or normal. Data analysis and monitoring are performed according to the broker entities, where progress sensor, order, and operation are updated with new events coming from both the data provider and the Internet of Things devices. Visualization and alarms. Visualization and handling alarms constitute an important front end for keeping track of the manufacturing monitoring system under development, providing crucial information to decision makers. While the visualization component allows the presentation of monitoring and other context-specific data, the alarms component provides indicators for visualization, sending messages under specific conditions, or activation of actuators, among others. Development and implementation issues. Development and implementation issues. This section discusses development and implementation aspects of the architecture components and the interactions among them, covering from Internet of Things and MES data acquisition to delay analysis and results presentation. Subscriptions and notifications. Each subscription must identify the type of entity to which it refers to and under what circumstances the component must be notified. As shown, data visualization requires full notification updates of entities' work center and operation, while for orders data must be previously processed by the delay analysis component before sending it to the application. Therefore, the subscription to the broker must be configured in order to filter the updates of interest, which, in this case, translates into the validation of attributes process delay, schedule delay, and progress. As for the delay analysis component, the entities of interest are of type order and progress sensor. While for progress sensor entities, no verification conditions are set high. All updates are relevant for studying operations delay. For order entities, not all updates are relevant for assessing orders delay. In this case, the updates only stem from the data provider, being the broker responsible for their notification. In addition, updates issued by data analysis are ignored. At this point you should be asleep, or bored to tears, or looking up the article for yourself because you can't imagine life without mastering whatever this is. Either way, enjoy, but I'm done here.